And I will start by introducing myself. I'm Estefania Barreto-Ojeda. I'm a computational scientist at Cyclica. Cyclica is a startup based in Toronto. I happily work remotely from Calgary. I'm based in Calgary. And I joined very recently after finishing my PhD. I finished my PhD in spring this year. And then I got this offer to join Cyclica as a computational scientist. Computational scientist is my role, but actually I do a lot of things. I maintain, I develop, and I also am part of the ML deployment solution at Cyclica as well. For today, I have a story that I would like to share with you because when I joined Cyclica, they gave me a task about starting to version data and version models for drug discovery. And it was a very interesting experience, and I would like to share this experience with you as well. All the content that I'm going to show today is available on GitHub, so if you want just to scan the QR code, you can find everything. And I aimed of this repo to be 100% reproducible. If it's not, please let me know. But the idea is that it will work. I hope it works. Okay, so let's start. So I structured this talk in order to have two parts, two main blocks. In the first block, I'm going to introduce biological data, and I would like to show you why working with biological data in machine learning pipelines is different. I would like to also highlight how that difference with biological data affects the development of machine learning pipelines, and how we should be prepared for data feedback loops, and what are the challenges we're facing. In the second part, I would like to introduce DBC and to show you how do we implement data version control and model version control in our pipelines, and also offering some highlights in the process. And I would like to start the first part by addressing something that is a building block in machine learning, that is data. And we have no machine learning pipelines without data. Data is fundamental. And you know, sometimes we have machine learning pipelines where we need a lot of data, and some other people that they are struggling because they don't have data. But in reality, for biology, we do need a lot of data, of course, but also we have a lot of data. And having a lot of data is sometimes very nice, but sometimes it's also very problematic because not necessarily we are translating from a large amount of data to the same amount of information. And this is particularly challenging in biological sciences overall. I don't know if you attended the talk for the speaker from the New York Times, and they were saying, oh yeah, we have first-party data. And I was like, oh, well, that's awesome. That solves a lot of the problem here. Well, we don't. Essentially, our data is something that comes from experiments. So we depend on basic science and basic research to access to this data. Now, biological data is complex, and the complexity of biological data is its nature. When we are developing some sort of research solution to answer a very specific question in research, we are at a point in science in which essentially whatever we do to answer our research question is extremely specific. So we have very specific experimental designs to find answers to that research question. Also, given that we are exploring every time further and further, this complexity is just increasing. On top of that, the complex nature of biological data, I would like to highlight 4 main points that make biological data very complex. These points are heterogeneous, high-dimensional, conditional, and research bias. And what do I mean with that? With heterogeneous data, I mean that biology, and when I say biological data, I didn't clarify it before, but I mean biochemical data, chemical data, purely biological data. With the boom of big data and having more access to technologies, we are essentially creating and generating more and more information. This is a very fast-paced generation of information, and also at different levels. We started with DNA, we started with 25,000 genes at the very beginning, but then things were just expanding, and then we ended up with the study of RNA, that is transcriptomics, and then all the big omics started to blow up, and then we got proteomics and then metabolomics. And even though this is very nice, because it means we have a lot of data, there is a very serious problem, and is that we have very diverse formats. And with that, I mean that it's not the same to analyze data that I got from DNA, that I got from proteins. And if I'm lucky, I will have sometimes that this information is overlapping, but if it's overlapping, then it's redundant. And also the fact that to study each one of these branches, I need very specific assays, so it makes the exploration of these data very complex. And it's also, biological data is also high dimensional. And this is a problem that is a very serious problem, and it's a very serious limitation when we work with biological data. And is that most of the times we have very low number of samples or observations, and we have a lot of features. And I don't work in genomics particularly. I deeply admire people that work in genomics because I think it's a very challenging problem that they face in that particular research field. But I would like to bring up here an example of Nature Review Cancer 2008, where essentially they have, in only one sample, they have 100 different tumors, but they are working with 1,000 samples. And then this is only one small part of the publication. And essentially they end up with, in the order of hundreds of thousands of features, which is really crazy. So in biological data, we are always working with high dimensional data. Now there is another, I would say, more problematic limitation here, and is that biological data is conditional. And with this I mean that even though we are taking this information from science, and science is supposed to be reproducible, sometimes it's not. And it's not because the protocols, even if they are documented, I am supposed to follow the steps. Sometimes there are technical reasons or environmental reasons, and I simply can't reproduce the experiment. And this is very serious because machine learning in biological data is using ground truths from experimental data. So if we don't have the ground truths, well, we are very limited. And there are several attempts, there are several intentions from several groups in the world, and they are trying to say, okay, fine, we have this problem, let's fix it. But how? Because it's not an easy problem to solve, and I would like to highlight here the workflow that is from a publication in Cancer Cell from 2020, where they are saying, well, yes, we have a problem, we need to standardize in some fashion our data. We need to make our data, the way we're aggregating and curating data, this should be somehow manageable, this should be standardized. We need a tool for it. But they also realized in the process, after proposing a very nice pipeline, well, yes, if we standardize, it's nice. We have some data that is organized, is standardized, but we lose information and we lose functionality. So it's a trade. We cannot go completely to let's standardize everything because we lose information in the process. So this, once again, is showing us that with complex problems, we have to develop complex solutions, and we have very, very, not only very challenging to, let the experimental design to have the microscope and all the pieces I need, but the interpretation of the results, it's very hard. And on top of everything, biological data is research bias. And this is also a very serious limitation we have because we have more data on certain topics. And those topics, sometimes they are because there is some federal grant that it will cover a very specific disease, and then I will just have this experiment running for this disease, and then I don't care about anything else. Well, PIs need grant, students need money, we all need the positions, the PhDs. So it's very usual that we find more information on certain topics. And I would like to bring up a very specific example here. I know we are all tired of this, but I think it's very remarkable with COVID-19 how this is a quote from a publication. It was an opinion article in Nature, and it was in 2020. It was December, and it wasn't really that bad at the time. Well, yeah, it blew up, but 2020 wasn't over yet. And at the time, this person found that there were more than 190,000 publications in COVID-19 by December 2020. And essentially, like, yeah, great, the world is working on COVID-19, but, well, I don't work with COVID-19, and I need to finish a PhD. So we all need data. And the truth is that we will always find more information on very specific topics when we talk about biological or chemical data. So, yeah, we have to work with very complex data. And the complexity of biological data, it's all over the place. We have to learn to live with it, and we have to find a way to work with dissimilar data, that they have different formats, different units, different everything, and even if they have sometimes the same experiment, someone wants to work in concentrations that are different, well, I don't care, that's not standardized, and if you want to use the scale of microliters or milliliters, it's up to you. So it's all work for us. We need to be sure that we're using the right everything when we work with machine learning pipelines. As I said before, we may have redundant because it's also duplicated, and we have to find it. It's imbalanced because it's also research bias, so we need to find something that it's balanced to feed our machine learning pipeline. And also, sometimes people are careless and they just need to publish, and that's completely understandable. I was in a PhD, so I just need to publish, let's put the data by, no annotations, I'm lost. Well, I need to solve it. I wrote a blog post on this topic for cyclic hours, essentially discuss these specific points as well. This is a QR code if you would like to read it. But my main message here is, even though in biological data, when we have lots of data, we don't have information. And there is a lot of work in the process to have pure data up to having the final piece of data that I will feed my machine learning pipeline. And I consider that data engineers in this field have pretty remarkable performance to an ability and talent to actually get all that ugly data up to a state where it's decent enough to fit in a machine learning algorithm. The fact that biological data has no direct user implementation and requires a ranger that is taking care of these data and say, okay, no, this is very bad, and I will fix you, and then now you can pass. This is a very time-consuming, and also it's very problematic in the long term for machine learning pipelines. And the reason is because these data that we are cleaning, standardizing, it's only the first step in a way longer process. And this first step, that is for the data engineer to have just the source and then the raw data and then make something out of it and have decent data, it's then going through the training process. And the training process in other type of machine learning pipelines is the type of machine learning that I have. Okay, I split training and validation set, then I put my model to train, then I validate, I get a ML model, I check the metrics, boom. Well, in biological data, and in particular for drug discovery, that step is very intense. It required a lot of computation, is slow, and usually we use deep learning, so essentially we need certain numbers of epochs to go back, forward, then train the model. We spent already a lot of money and time on our virtual machines training everything. Finally, we have an ML model, and then the metrics are bad. And then we have to go back and optimize and start the process again. And then, let's say after a lot of work, I get my machine learning model, and then I say, okay, fine, I'm happy, my manager is happy, let's ship this. And then we can deploy this via an API or an application, and that's not it, unfortunately. These machine learning models tend to get obsolete very quickly, in particular in drug discovery, and this is, again, very problematic, because in machine learning for drug discovery, what happens is that I work very hard, I have my machine learning model, I have it ready, and then AlphaFold appears with 200 million data. And my pipeline has to be strong and solid enough that I can guarantee that I can go through my raw data, curated data, my machine learning model that it took forever to train in my deep learning, And then I have the metrics. Finally, I'm happy, and Meta publishes, again, millions of structures. So my pipeline has to be strong enough, but also flexible enough. And this is problematic because how do we track all of this? How do we do to essentially track every single step? Because in contrast to the standard software development, Git is not enough, first of all, because Git is tracking code, but also it's not about, we have a given library, we are testing, we have a unit test, we have 100% coverage, boom, we have an application, that's awesome. Well, that doesn't happen in machine learning, unfortunately. In machine learning, we are dealing with not only the complexity of the data, that is very, very complex, but also with the complexity of the pipeline itself. Because machine learning pipelines in drug discovery is this combination of my initial data, the curated data, the ML model that I'm creating, the metrics, and then the new AlphaFold I have that I need to put in and create a new model and avoid getting obsolete. So on top of everything, each time that I run the steps 1 to 4, I'm running one single experiment. And I need to keep track of how did I modify the data, because if I modify the data differently, then I'll have a different model, therefore different metrics. How do I keep track of all of this? And also fast enough that I can move with the new publications and new data that is available. In particular, to track raw and curated data, ML models, and metrics. And also, if I am keeping track of all these points, then how do I improve the prediction? Because at the end, what we want to do is having a more accurate prediction, and all this work is just to increase our prediction and our metrics. So how do we track all these changes? I'm already tracking the code with Git. So how can I solve this problem? So one of the solutions we identified is DBC. With this, I would like to start the second part of this talk about implementing data version control in drug discovery pipelines. And DVC stands for Data Version Control. It's no Disney Vacation Club. Every time I Google DVC logo, I get Disney Vacation Club, so no. Something that I really like about DVC is that it's an open source project. I don't know if I already mentioned, probably yes. I have a background from academia, and I really appreciate when people can identify problems, and open source is the best platform for it, because somebody else can see what I cannot see, and vice versa, I can see what other people cannot see, those bugs in the code. So it's an open source project, so we can go and check and try to find some bugs if there is any. It's compatible with Git providers, so it doesn't matter if I'm working on Bitbucket, GitLab, or GitHub, it will work. It's also compatible with cloud search providers, so regardless of who you prefer, it's available for you. It works for Google Cloud, for Amazon, for Azure. It's very nice, and also something that is very important is that it's language and machine learning frame agnostic. It means that if tomorrow I decide to change my approach from Python to Julia or from Python to R, I can do it with DVC. And I don't need to go crazy about it. I will just have to update my DVC files. But I can keep working on it. So what can DVC do? What DVC does is to track very nicely all the files that I'm generating, data files, models, and metrics. And also, it helps me to version control my ML projects. So not only one step, not only one file, but the project itself. And also to manage them, because it's huge. And we're going to see some examples of it. So I'm going to go through the very basics just to give you an idea on how I started and how I think everybody starts. And we have to just install DVC. In the repo that I provided, you have the requirements there. So if you want to install DVC all, that will have all the providers, please feel free to do so. And just please confirm that you have your requirements there, because otherwise we cannot do anything here. And I have my DVC requirements that are ready to run here. And then what we need to do is to have DVC initialized. DVC initialized is important because also it sometimes will tell you, hold on, you don't have Git already. Are you sure you want to do this? And even though working with DVC, it's recommended to have Git. It's up to you if you don't want. But we lose functionality, kind of. We cannot take advantage of the full functionality of DVC without Git. So we initialize DVC init, and I'm going to, hopefully I have something here. That if I initialize DVC init, they will say like, are you sure you want to do that? That doesn't sound like a good idea. And I say, okay, fine. I will then initialize my Git and then do it. And then DVC says, okay, fine, now I'm ready. You can now commit your changes to Git. And I will start just here in my local repo because I don't want problems. And now the thing is, what are we doing really? What are we initializing when we have DVC? And yes, because it's demo 2 here. So essentially what I create is hidden files for DVC, DVC ignore, and Git, and it's very similar as what we have in Git. But the DVC folder has a config file, and there is nothing there. Oh, yes, because it's demo 2, of course. There is nothing there in this file. But what can we have in this file? Well, it's a configuration file where essentially we can set our remote. And even though DVC doesn't really ask you to have a remote that is the cloud, it's recommended. So you can have a remote that is not remote, it's local in any other directory if you want to choose it. And then after you set your remote, then you have ready a URL where essentially you can send all your information. And then if you have no idea what do you have, then you can list that. And also you can set a default, because if I have so many, like in my case, I have 5, 10 different remotes. I'm sending information to different places, but I want to set one default, then I can set the default very easily. And then what I can see here is that my config file now essentially has a core where it has the default remote, and then I can assign whatever I want to that remote. So if I want to assign something broken, free to do it, and if I cannot push the files, well, I knew that wasn't possible. So then the next step is to start tracking a file or a directory, and essentially what we do is DVC add the file and the extension. So I'm going to just, for the purpose of this talk, just to show what I'm doing here. I'm just printing, this is a test file, and I'm just DVC adding that simple echo that I have. And let me do something like this. And essentially, DVC is telling me, okay, so you can now add this file. Also, we have a git ignore, and they have the message, or you can auto-stitch if you want to add as soon as we have DVC add, if you want to do it. But when we are adding files, we are doing 3 different things. The first thing we're doing here is to create metadata. So if we check our folder, what we're going to find is that there is a DVC file extension, and that file will contain metadata. This metadata contains the MD5 hash associated to it, and it will have like the size as a checkpoint and the path that is in the name of the file. And why is it not running here? So when we explore the cache, because that's the other thing that shows up when we create, when we do the DVC add, is that there is one piece of the cache that was added, and essentially it corresponds when we check here, and I will check here on my screen that it is here. When we check here the MD5 hash, essentially we have the DVC cache that is split into folders that have the very first 2 characters of my MD5 hash, and then the name of the file that is the rest of the characters. And then when I have that file, I have my file there, and I can retrieve it with that MD5 hash and the metadata. And the third part that I get is the git ignore, because what DVC wants me to do is to say, okay, track your DVC files as metadata, but don't track the actual file, because Git will collapse. And then when we check here, our git ignore essentially is the extension that I have. That can be any extension, and then I say, okay, so now after this, I can git commit, and I will delete this just for not have my repo here messy. And after we do the DBC add, essentially we generate a DBC file, we add the item to the cache, and then we add files to the git ignore. And then the next step is to commit our DBC files and our git ignore. And then what we are doing with Git is subtracting that metadata, not the file itself. So now that we have the basic setup and we have the basics, we know how to install, initialize the remote, and we have a test for adding a file. Let's see how it really works when we have data versioning. So for this exercise, I will assume that in this very complex data pipeline, I'll have raw data, created data, ML models, and metrics. So for this purpose, I'm going to say, well, let's assume I have the initial data that is in the repo, data initial data, CSV, and I want to build a pipeline that has 3 steps, just to simplify: featureization, preparation, and training and metrics. So if you check the repo in the source, you will find that we have 3 Python files that are ready to perform these operations for featureizing process string. Please don't focus too much in the code, first because it's not high quality code, I just want something working. And second, because here the point is to identify that for every step that I have in my machine learning model, I can actually modularize that part and work together with DBC. When I have this type of structure, what I want to do is to manage a way to record and reproduce each particular step, every single step that I have, from the moment I have my data to the moment I have the metrics or the model. And let's see, how do we do? I'm going to do a very quick, less than 1 minute, I promise, EDA. So essentially we have here information with smiles and class. Smiles are essentially a string representation of a molecule that is human and machine readable. It was, I think it came out like in 1980s, but it became more popular after 2007 with the RDKit that is a package for human informatics and for machine learning. So our data are essentially smiles and labels. That's all what we have. And just to give you an example, we can have this, for instance, the representation of one of the smiles we have there that we can then check with other cool libraries. What is the name? This is amitriptyline. Amitriptyline is a drug that is used mainly for to treat depression. So yes, it's a drug. And what I want to see is if I can say what is the toxicity. I'm specifying toxicity here. And let's start with the first step. I want to version the very first version of the data, my initial data for this pipeline. So I do my DBC data, initial data CSV. And then what DBC is saying, okay, I'm going to check the cache where you're working on. And then if it doesn't exist, I will add it. And so it's adding. And then it says, okay, I'm ready to go add this git ignore and the DBC file. I won't do the git commit at the moment. I will just continue here with my pipeline. So as I said before, we have 3 parts of featureization, preparation, and training metrics. For the featureization part, so we have always options. We can be messy, we can write better code, we can write modular and documentation. So we can go for this option that is essentially a Jupyter notebook where we have all our code, or we can be better citizens in the world and we can have something that is more modular without being perfect. So what if I have some sort of Python code where I can featureize my data, and then I just have an input file, and an output file. And what if I can additionally add some parameters from a YAML file that then I can modify just from the YAML instead of, like going to the notebook and then iterating over and over. And this is where DBC comes very handy, because DBC offers the option to create pipelines by steps. And it also offers the option that in each one of those stages, we're going to parse specific parameters from a YAML file. And on top of everything, I can run step by step that part of the pipeline. And that is only 2 commands, DBC stage add and DBC repro. So what do I want to do? If I have initial data, I have already the code to featureize, and I want to pass parameters, I just want to create one stage in my pipeline that essentially will have these different flags. I will have this name for featureize. I have dependencies that they are labeled here with the -d flag, and then the Python code that I want to execute, the command line. And then when we run this, and I really hope it works, so it works, it's creating a stage that is called featureize. And what DVC is telling us is saying, okay, I'm creating this DVC YAML file, and I'm adding the stage featureize in the DVC YAML. So I'm sorry, I'm just going to go through the next one because I need to run this, and it takes time. And yeah, here. So what do we have here in the DVC YAML file? What we're going to have here is essentially the information of the stage that we have. What is the name? What are the parameters we are passing? And what is essentially the command line that we are running. And yeah, you can tell that I'm running something here. And it's done. Okay, so we can have a very readable file that is telling us what I'm really doing in the featureize part of my pipeline. Then once I have the DVC repro running here, what I'm going to do is to add the featureize data. And this featureize data will tell me, oh, okay, so you're adding another file because I didn't find it in the cache. It's ready to go to Git here with the git ignore and with the DVC. And if you are tired of me telling you that you should add this, I can do it by myself if you auto stage through, which I won't do it at the moment. So then I will run this step in the pipeline. That is, I just said previously here, so I just need DVC stage add and DVC repro to get a running step in the pipeline. So that's how we version data. And that's it? Well, no, that's not it. Actually, DVC has very cool features, and one of my favorites is DVC DAG, that is a directed acyclic graph. And what we have is a cool ASCII plot of what are we doing in our pipeline. So essentially, the stages that I just defined with DVC stage add will be a node, and whatever the dependencies we have, they are edges. And for instance, what I have here is that I already started with an initial data, and I'm going through the featureize stage, and the featureize stage will give me an output file that is also DVC, this version control. So I already have the first step of my pipeline where this is version. Now, the second part is processing, and this is very common when we have a drug discovery pipeline because we need to remove all the features that are meaningless, that are not providing information, also to remove the correlations, and then again, I can be messy and have just a Jupyter notebook, but I can do better, and then I can have this command with Python that essentially will take my input file, that is the output from the previous stage, and the process data, that is the output from this stage. And I want to parse parameters because what if I can improve the performance of my model when I change the threshold, all the filter that I'm using to remove those features or to remove correlations. So what I'm going to do now is a DVC stage add, and I had this for the new process part, and it's telling me, oh, okay, I'm adding this process stage in our DVC YAML file. When we check here, what we have is that, yes, we have a new block of code that is telling me what is executing, what are the dependencies, and what are the parameters. And DVC has another interesting feature, that is that I can either reproduce all the parts of my pipeline or just one. With DVC repro, we are reproducing all what we have in our YAML file. So essentially, this is telling me, it's saying like, oh, okay, so you were having an initial data, but it didn't change, so I won't even spend time on this. I also found a featureize stage, but it didn't change, so why would I even bother? But there is a new process, a new stage, sorry, that is called process, and I will run it. And I'm using these two values, and I'm creating this log file, DVC log. We should pay attention to that. And then when we are ready, we add our process data CSV to version the output of this stage of the pipeline. And before I don't give more attention, don't pay more attention to this, the DVC log file is very important. And this file is extremely important because essentially it's defining what is per stage of your machine learning pipeline, what are the files that are associated to it, what is the MD5 hash associated to it, the size that is the checkpoint, the parameters that are associated, and these parameters that are included in the params.yaml file. And the same goes for each one of the stages. So it's not recommended to manually edit this file. This is something like a protection type of file. And DVC can do better than us because we can make more mistakes. That's something that is fully automated. So I recommend not to touch. Every time that we are generating a new stage in our pipeline, this is going to update. And then what is left is to have DVC stage add. So most of the times in the machine learning pipelines, one of the most critical parts is how do we split our train and test set? What seed are we using to make it reproducible? And when we have regressors, the number of estimators we have. And this feature that I'm adding here, the feature is max number, is because the data set I'm sharing with you is bigger than 2,000, and I want it to be quicker. So it has only 2,000 samples. And the idea is that in this stage of the pipeline, then what I'm doing is I execute the train.py. I take the process data, which is the data I'm going to use to train, but I want two outputs. I want to have the model, because I want to version that, and I want to also know what are the metrics, because I need to know what is the performance. And then after I execute this, and let's see here, it's saying, okay, fine, you don't have a stage that is called train, so I will add it. And this is all ready to go in your new DVC YAML file. And when we check here, we see that our DVC YAML is all in order. You have the commands, dependencies, parameters, and then we can DVC reproduce. And what we are doing here is, let me close this. What we are doing here with DVC repro is essentially running every single stage of our pipeline without editing our code, which I think is amazing. And as you can see, it's saying, okay, I'm running the stage train because everything else is all ready. It's all done. So essentially, I have here, this is a printing message from the code saying, okay, have this number for the training set, for the test set, what is blocker, non-blocker, for my compounds. Then I have the whatever metrics I want to have. And what I'm doing also here is check the source code. What I'm doing is export into a JSON file the score for my model, just because I want to. And then DVC is very smart here in this case. It's telling me, you know, don't even bother because the featureized process is done. The process part is done. All what I need to do is to run the very last stage of this training, and it's done. And then the very last step is just to add the two output files of my output, that is essentially what I got from metrics and from model, and the DVC tag, that is one of my favorite, it's here. Essentially, we have a diagram with the full pipeline that is telling us which is the input data, where is it going, where is the output data, and how can I find it. And I think it's very useful. So essentially, we have authorization, processing, training, and metrics. And then the last part is to run DVC experiment run. And DVC experiment run is to run the full pipeline. And DVC will tell us, oh, because I ran it before, that's why. But I can't say, actually, hold on. I can just force it. And then, yeah, don't do it for your actual pipelines. And then it will say, okay, fine, I'm going to run the whole experiment. I'm going to run whatever is needed to do. So I will run the process, I will run the visualization, and I will run the training. And then this is giving me essentially all the results from my model. Now, isn't this cool? I think it's super cool. And I just wanted to show how nice it is to work with this type of tech. in comparison to previous years, where essentially it was so hard to work with this. And yeah, so probably that's probably myself in the past in another life, and now me enjoying working with machine learning and DBC. There are some highlights that I would like just to mention, in particular as a user, not as a developer. I love DBC, but I'm not a developer. I would like to, but no, I'm very busy as a computational scientist at Cyclica. But there are more. We can track data, models. We can manage experiments, reproduce and compare. We can also add custom metadata. There is a Python API. They have amazing documentation, and I'm kind of a fundamentalist about documentation. Their documentation is awesome. They have a plugin for VS Code. It's a very interesting project. So if you're working with machine learning projects and this type of data, just check it out. So just to close, DBC is a very valuable tool for machine learning workflows and in particular in drug discovery. And we can run away from the complexity of data because that's nature and data is complex, but we can learn to manage it, and DBC is a very good option. So thank you very much. I would like just to thank all the people in my company, well, the company I work for, the CEO, Nahid, and Stephen McKinnon, who is the CSO, and Ali and Steve that gave me this particular task, and then they say, okay, enjoy DBC, and actually I'm enjoying this journey. And my team that is very nice, with Marilena, the team lead, and Federico and Daniela, which we really enjoyed our discussions about machine learning and data version control. And thank you very much. If you're interested, this is the GitHub repo. It's reproducible. I checked. And the blog post. And thank you very much.